Vanakkam. Welcome to this video on biomedical instrumentation. We have been looking at various sensors used in biomedical instruments, types of various types of sensors, and in the previous video, we looked at pressure sensors, for example, using capacitive sensors, for example, pressure sensors and other sensors using capacitive design. In this video, we will focus our attention on inductive sensors. We know from high school that the inductance of a material is dependent on multiple things. One is the number of turns of a coil that is wound, the cable that is wound. The other is its geometric form factor. And then mu is the permeability of the medium. Note the difference between permeability and permittivity, a fundamental difference. And L is the length of the coil. The inductance capital L is used to is essentially an indicator of a displacement that is happening when any of these three things change, either the number of turns or the geometric form factor or the length. If any of these three things are changed due to a mechanical change that happens, you can use that to measure displacement, by how much displacement is happening. Critically, note that these sensors are not affected by the dielectric or insulation or insulator property of the environment. Rather, they are affected by magnetic field, because these are coils wound around a core. They are affected by any stray magnetic fields. There are different types of these inductive sensors that are used for various purposes. These types are self-inductance based sensors, mutual inductance based sensors, and differential transformer type sensors. Now, self-inductance based sensors usually have a coil and a core that is moving, a movable core. Now, if the core is moving, then it causes a change in the inductance. But that means that output and the construction is relatively simple. But the problem is that the relationship is not linear. The other idea is to use two coils, one primary and one secondary type. In this case, the relative position of the coil, one of these coils move relative to the other, thus affecting what is called as a mutual inductance. This alters mutual coupling between the two coils. This is a great method. This is also linear, but the problem is that this requires you to tune the two coils to some resonance, right? Because it needs resonance tuning. The third and the most critical and the most important, critical means important, the most crucially and most prevalent approach to measuring displacement is the so-called LVDT. What is LVDT? Linear Variable Differential Transformer. LVDT means Linear Variable Differential Transformer. This one has one primary coil and it has two secondary coils. So the total number of coils is not two. In the first case, in the self-inductance case, there is only one coil. In the second mutual inductance case, there are two coils, one primary and one secondary. In the third case, LVDT, there are three coils, one primary coil and two secondary coils. Now, it essentially induces equal voltages in two secondaries, in the dual secondary coils, when the core, usually the core is made of a ferromagnetic material, and when you keep that core in between at the center of the two secondary coils, it will essentially induce equal voltages in the two secondary coils. But when the core moves relative to the two secondary coils, accordingly the voltage induced as a proportion of the total voltage will change, giving a relatively accurate and linear representation of displacement. So let us say a displacement of core by some amount, say d, happens. The differential output between the two secondary coils is essentially a function of the displacement with some proportionality constant k. So if the displacement is d, the output voltage VO or V naught is usually kd. Of course, we need to determine k, but that is quite trivial. That is a matter of calibration. You could find k by using a calibration routine. You could find k, and then once you find k, that k is not going to change. A great advantage of this approach is that it is linear. Or actually, LVDT by definition is linear. It is quite often used in in biomedical applications. Often it is used to measure displacements, pressure, forces, and it converts the linear displacement into the directly into a voltage signal. That is convenient because I can immediately convert it into, for example, into a digital signal, which I can then use to process. It consists of one primary coil and two secondary coils, as I mentioned. The great advantage is that it is highly linear and has a moving core. And it is the position of the core that influences the coupling between the primary and the secondary coils. If we are measuring the differential output between the two, and if the core is exactly at the center, the differential output between the two will be exactly zero. But when the core moves in either of the two directions of the either of the two secondaries, accordingly, there will be a greater voltage induced in the secondary towards which the core is moving. This change in the direction is, suppose it is changing a direction, there will also be a phase reversal that you can observe in the voltage. Critically, the linearity is a grand advantage. It is highly sensitive, so the accuracies are very high. And if you use captive design, for example, if you use captive design, then it usually has frictionless operation because there is nearly zero friction, and it can be used to make measurements for a relatively large number of times and nearly an infinite mechanical life. So quite frequently it is used in intra-aortic balloon catheter pressure sensing. Quite often that is an application of the LVDTs. Another application is in measurement of arterial diameters. Note that arterial diameter will change as a function of where in the circulation cycle the artery is, because arteries and veins both are compliant tubes. They are not rigid bodies. They're compliant tubes. So the diameter will vary as a function of blood flowing through it. Also, LVDT can be used to measure kinematics, joint kinematics, or movement analysis. And it can also be used to measure muscle movements, displacement of muscles. A key design consideration is to use captive core design. What is this captive core design? It is essentially a situation in which the core or the magnetic core or the armature, for example, in a motor, you would call this as an armature. It's not exactly a motor. Here in this case, we call it as a magnetic core. So this magnetic core is physically constrained to move within a specified dimension, so that it cannot, even when the whole system is displaced in multiple directions, the core can, or the core movement is restricted to a particular axis. And if you use hermetic sealing, what do we mean by hermetic sealing? Hermetic sealing is a situation in which is the object, in this case, because it is only, we are only interested in magnetic coupling, the core itself is inside an airtight compartment. So that means I can also insert it inside a fluid, like for example blood, and then the movement will happen inside, and there will be no blood entering inside, or nothing from inside the armature or the core will go to the blood, but still the movement itself can be detected, for example. So if you use hermetic sealing and captive core design, a design in which the movement of the armature or the core is restricted to a particular axis, then you are going to have an extraordinary amount of accuracy, linearity, and nearly infinite mechanical life, because there is minimal friction. The advantage is that this will be airtight and watertight, and because the seal is going to protect the core, there is going to be no corrosion or no disturbance to the core itself, giving a huge or a very long shelf life. So it will be highly reliable in harsh environments such as the human body. Remember, the human body presents a harsh environment for measurements, electrical measurement systems such as these. So quite often we use this sort of hermetic sealing and captive core design to improve the shelf life, to improve the frictionless operation. Another advantage is that there will be no contact possible. It is impossible for the core to ever come in contact with the coils, thus preventing absolute electrical isolation. What is happening is only magnetic inductance or magnetic coupling, but there will be zero electrical contact. Now that ensures that there is no electrical wear, so there is no mechanical wear, because this is happening in a frictionless environment in a captive core with the hermetic sealing, and there is no electrical wear because there is no electrical contact with the coil, for example. And this such captive core design also ensures that there is no misalignment or changes, because if there is a misalignment, then it is not that the system will not work. If there is a misalignment, the system will still work, but you will have to recalibrate it again. So such a possibility of misalignment is very low in what are called as captive core design and hermetic sealing. So, and for biomedical applications, we are looking at LVDTs that are really small, and there are such devices available, because we are many times we are interested in measuring displacements and pressure in a catheter. Catheter means you are looking at sub 2 mm, sub 3 mm sized systems. So you are looking at miniaturization. So biomedical LVDTs that are used, by the way, LVDTs are used in various industries, not just in biomedical applications, but the one that we are interested in is for biomedical or healthcare applications. They should be really compact so that we can use them in catheters or in implanted devices or surgical devices. So because there has been an extraordinary improvement in winding technology, it is possible for us to design really tiny, extremely small, lightweight LVDTs that have hermetic sealing and captive core technology, providing really small but extraordinarily accurate and linear LVDTs. The other thing is that if it is going to be, other consideration is that if it is going to be placed inside the harsh environment of the human body, that is, if, for example, if you're interested in measuring the displacement or pressure inside the cardiovascular system, for example, using a catheter, then you need to consider biocompatibility. You need to use materials that are inert, that do not react with blood, for example, or any other fluid or any other material of the human body, inside the human body. So we need to use materials that are medical grade. That could be medical grade stainless steel, that could be titanium, platinum, or medical grade polymers, for example, so that they can be used for relatively long term implantation. I already mentioned about hermetic sealing, and importantly, to ensure that there is no mechanical wear and tear, we need to use low friction bearings. So, captive core design, low friction bearing, hermetic sealing are all critical in the design. The other design consideration is that we can, for example, use signal conditioning unit within the LVDT system itself, so that we minimize noise at source. So the LVDT housing itself contains really small analog signal processing system that then maybe converts it into digital form and then transmits digitally, for example. That way you will get output that is digital directly, and you can, for example, read this data through, say, for example, Wi-Fi or Bluetooth, for example. It will be great if you can if we can also try and enable systems that have analog or digital processing systems that compensate for any possible temperature drift. If you know what the application is, where you are going to place, you could design for specific sensitivity and specific requirement. So the advantage is that this is linear over a relatively large range. It provides an excellent linearity, and it is highly reliable and reproducible. It gives high repeatability and reproducibility, and have excellent resolution. It supports sub millimeter resolution, sometimes even resolutions at tens or hundreds of microns, which is an excellent resolution. So in modern adaptations, we use miniature or custom LVDTs that are made for specific biomedical applications. Note that these kind of devices cannot be used in other biomedical applications. So because we have these micro fabrication techniques, you cannot use these in other biomedical devices. If you design for a particular function to be implanted in a particular body part, to be implanted in a particular organ, to make a particular measurement, they are quite useful. So, that way, it is specialized, but It will work only in that environment. And usually, because of advancements in materials technology, these devices are housed within biocompatible systems. So that way they will be robust and they will not be harmed by the harsh environment within the human body. They are usually dynamic and these systems have very high bandwidth. So usually, because both electrical and magnetic wear and tear is highly restricted, they are low maintenance and have high reliability and a relatively long shelf life. So the future in this field is on, I already mentioned this, is to come up with ways and means through which you could have a signal processing system within the measurement system itself, then convert it into digital and then maybe transmit it through Bluetooth or wireless. Perhaps, if possible, to power this LVDT itself using, say, the movement of the body itself, say, for example, self-powered LVDT, for example. These are futuristic designs and still we need to design this. And really micro and nano level, really small, extraordinary small and nano and micro level. That way we can measure at tissue or cellular level scales, supporting. That way we are able to perform research, enabling research at micro or nano level to be used in lab on chip type of devices, for example. And then the other idea is to use a closed loop system, use this sensor as part of a closed loop system to use in some other control loop. The other idea is to use AI or machine learning type of approaches to allow the LVDT to self-calibrate, for example, self-calibrating systems. So these are the future approaches towards using LVDT. In conclusion, in summary, what we are looking at is that LVDTs are high resolution, highly reliable, and excellent linear displacement sensors that are quite often used in biomedical systems. And the current modern designs essentially focus on miniaturizing, making it micro and nano sized, providing high resolution at sub millimeter, maybe tens to hundreds of microns resolution, providing high level of biocompatibility, providing excellent packaging, ensuring captive design, ensuring hermetic sealing, ensuring having low friction bearing so that mechanical wear and tear is prevented, so that magnetic wear and tear is prevented, so that electrical wear and tear is prevented, and all that. So all this and the future outlook is to have, say, digitally communicating, having a system or a chip that processes the LVDT data, that performs signal conditioning on the device itself and then converts it into digital and then transmits it wirelessly, for example, to the outside world. Maybe the future of this. So LVDTs have been improving since their inception, but the future outlook involves miniaturization, digital transmission, and other such challenges. Critically, they can be used for personalized and tailored diagnosis and therapy. But note that it is, if you design an LVDT for a particular application, you may not be able to use that LVDT for a different application in the same human. So, in that sense, you are going to have high linearity for that application. So again, everything depends on design. So with this, we come to the end of this discussion on LVDTs. We will stop this recording and we will continue our discussion on other topics such as piezoelectric sensors, Hall effect sensors, and others in a little bit of time. Thank you very much for your attention.